Hey guys, welcome to Unit 9 Note C. Today we're going to learn about something called enthalpy and see how it can help us determine the heat of a reaction and how that relates to some balanced equations. So all about enthalpy today. So what is enthalpy? Enthalpy is a type of chemical energy. It's a heat energy. But as opposed to just calling it heat, which you could do for anything, an ice cube, a hunk of metal, as we've done in calorimetry, when you're talking about the heat energy of a chemical reaction, we call it enthalpy. So it actually has a special symbol, delta H. Delta H can come in many different forms. We've talked already about heat of solution, heat of fusion. So when we're looking at the heat of a reaction or the enthalpy of a reaction, we're going to use the subscript to show that we're looking for that enthalpy of reaction. We'll talk about other enthalpies too, like enthalpy of formation. So instead of using the RxN there for reaction, we could use an F there to show us the enthalpy of formation. So all different ways just to show that we're looking for heat energy for a reaction. Typically this is going to be in kilojoules per mole, but we always want to watch our units. You may have some questions where they're giving you joules, you have to convert to kilojoules. They may not give it to you per mole, we may have to convert gram to mole. We're going to look at some different things that come up as we do some problems. But generally speaking, you want your enthalpy in kilojoules per mole. That's our heat of reaction. So the sign for delta H is actually exactly like the sign for Q. If the delta H is negative, just like if the Q is negative, that's going to mean it's exothermic. So that's releasing energy, giving off heat. And so you're going to get that negative sign for the delta H, just like you got the negative sign for Q. There's one other way to tell if the reaction is exothermic, and that's by looking at a graph. If the beginning of the amount of heat energy, the reactants, actually show that they have more energy than the products, well, we must have lost heat, right? For the reactants to have more energy than the products, we must have lost heat along the way. And so that's going to indicate that it's exothermic. When we get into our next unit on kinetics, we're going to look at this graph a little bit more. There's actually a lot more going on in the middle here. But for right now, all that we really need to focus on is that if the reactants have more energy than the products, we've released heat along the way, making it exothermic. We can also look at positive delta H's, which of course would be endothermic, meaning that they're absorbing energy. We're adding heat into the reaction, giving it that positive sign, just like we had the positive Q. And the graph of this heat energy would show that the reactants had less energy than the products. So how did the products end up with more energy? They must have gained that energy, making it an endothermic reaction. There's one other way to tell if we have an exothermic or endothermic reaction, and that's by looking at something called a thermochemical equation. So just like regular chemical equations, you're going to have reactants and products, but now they're going to include heat energy, hence thermochemical equation. So we still want them balanced, we still want our mole ratios, but now we're going to be able to use those coefficients and compare them to the amount of energy either being absorbed or released. So if the heat is released, that would make heat a product, and we would literally write it on the product side, indicating an exothermic reaction. Whereas if heat is a reactant, that would indicate it needs to be put into the system in order to facilitate the reaction, making it endothermic. We would write that heat energy on the reactant's side. So let's just kind of recap how to tell if it's an exothermic or endothermic reaction. The exothermic reactions will have negative Q and delta H's. The enthalpy or the heat will be negative. That goes with endothermic. We're also going to be doing a lot of word problems. So you want to keep an eye out for certain words that would indicate that we're releasing energy. Saying heat is evolved, it is produced, so anything that we're giving off heat, cooling, things like that. Looking at the thermochemical equation, if it's on the product side of the reaction, you can tell that it's an exothermic reaction. And then the graph that we looked at showed that the energy overall decreased. The reactants had a higher energy than the products. The reactant energy was greater than the products. On the endothermic side of things, we would have a positive delta H or Q. You're looking for words like absorbed, takes in, uses, heated, and the heat would be on the reactant side of the thermochemical equation, on the left-hand side. The graph would start off low and end up higher, with the products having more energy, so the reactants would have less energy than the products. So we've got to be able to look for signs of whether it's exothermic or endothermic and kind of make connections. For example, if I can tell because the heat is on the product side that it's exothermic, then when I use the delta H, I want to make sure that I'm using a negative delta H. So this is kind of a good chart to have readily available so that we can make those connections as we start working problems. It matters whether it's exothermic or endothermic. All right, so let's focus on these new thermochemical equations. Basically, it's a balanced equation that includes the enthalpy, that includes the delta H. And the sign is just like Q. If it's a positive delta H, it's endothermic, and a negative delta H would indicate that it's exothermic. So here's an example of one type of thermochemical equation. Off to the right-hand side of the equation, notice how the chemical equation kind of stops at one point. Off to the right-hand side, they're giving you that the enthalpy is equal to negative 890 kilojoules with the 3 significant figures. Another way to write this, like an alternate form, would be to keep my reactants. I'm going to skip the phases for right now. Keep the reactants on the left and the products on the right. But then I want to bring that delta H into the equation. The fact that it's negative means that it is exothermic, which means that I want to write that energy on the product side. So we're going to produce an additional amount of energy of 890 kilojoules. It's a very common mistake to use the negative sign in the chemical equation. Think about all of the balanced equations that you've ever seen in your life. Have you ever seen a negative sign in an equation? No, that's not how you read equations. The way this would read is that our CH4 and the O2 produce or yield the carbon dioxide and the water and this energy. So that is an and word. We're producing our products and the energy. Now, if we were going the other way around, the fact that it's on the product side means that when you write it as delta H equal, you need to make it negative. So you want to get kind of comfortable going back and forth between the two, because when we actually work problems, we want to make sure we're using the correct sign. And sometimes where the heat is in the equation can tell you what the sign should be. If it were a positive 890, we would write that on the reactant side. 890 kilojoules plus the reactants would then give the products. But it is negative, so we only want it on the product side. So negative goes on product side, positive on reactant side. The other thing we can take from this, given either way, whether they actually write it as delta H or whether they write it inside the equation, is to get a mole ratio out of it. Remember the coefficients told you the relative amounts? For example, one CH4 molecule reacts with 2 O2 molecules in order to make my products. So if I have the number of moles, I can make them proportional in the same way that I can make a certain number of moles proportional to this amount of energy. So we can make mole ratios out of any one of the 4, like either reactant or either product, we can set equal to the amount of energy. So if I've got 2 moles of oxygen related to that amount of energy, my ratio would look like this. If I was interested in the methane, I only have a coefficient of 1, so it's only 1 mole of the methane that's relative to the negative 890 kilojoules. Notice the sign is important to incorporate into that mole ratio. So the mole ratio is now going to become part of our conversion process. We can tell, for example, 1 mole of the methane is proportional to this negative 890 kilojoules. So what if you had 2 moles of methane? Then how much energy would you produce? Well, combustion of 2 moles of methane would produce twice as much energy, or 1780 kilojoules. So if I had 3 moles, I would get 3 times the amount of energy. It's all about the proportion. And that brings us to the first rule of thermochemistry. The magnitude or the amount of heat energy is directly proportional to the reactant or product moles. So if I have twice the number of moles involved, I would get twice the energy. If I had half the moles, I'd get half the energy, and so on. So we want to be able to kind of use this as a conversion factor to solve problems. So let's look at this first equation and kind of break it down a little bit before we dig in. Right now I have coefficients of 1 for my hydrogen and my chlorine, and a coefficient of 2 for hydrochloric acid. So that would mean 1 mole of either of my reactants is proportional to my enthalpy, or 2 moles of my product would be proportional to that amount of energy. Notice that the enthalpy is negative again, still meaning that it's exothermic. So we want to make sure that we consider that when we use the enthalpy in the conversion factors. Basically, what I can see from here is that I'm interested in chlorine, and the balanced equation tells me that 1 mole of chlorine is proportional to negative, don't forget the negative, 185 kilojoules. The question is asking me, okay, fine, but how much energy would it be if I had 1 gram? Which sounds a lot like a proportion, right? I have this amount of chlorine equaling this much energy, so what if I had this other amount of chlorine? Now how much energy would that be? And it is totally fine to solve this as a proportion, but it can get a little confusing where you have to do some side calculations here, because in a proportion you have to have like units. So we couldn't have moles of chlorine on the top and grams of chlorine over here on the top. We would have to either make them both moles or both grams, which is fine. Then you can cross multiply and carry on. But I want to show you, in my opinion, an easier way to do this using dimensional analysis skills. So we're starting with the 1 gram of the Cl2. So I would consider that my given, 1 gram of Cl2. I can tell from my balanced equations the number of moles. So the first thing that I want to do is get out of grams and into moles, which is our standard mole ratio, putting gram on the bottom and mole on top. Still of the diatomic chlorine, 1 mole is always equal to the molar mass, and for our chlorine, that molar mass would be 70.90. So now I'm in moles of chlorine. So here's my new conversion factor. From the balanced equation, I find my chlorine, and I can tell that I have 1 mole of that. So I'm going to be able to use moles, and I can tell from dimensional analysis that it's going to go on the bottom. But now I can also set that proportional to kilojoules. So just like we had mole to mole, you can now go mole to kilojoules and vice versa. So how many kilojoules? It's this negative 185. And how many moles is still my coefficient of 1 in this case. So I'm going to do 1 divided by the molar mass of 70.9 and times that negative 185. So notice that the sign is going to dictate the sign for the answer. If I have an exothermic reaction, changing the amount is still going to have an exothermic amount of energy being produced. So let's go ahead and type this in the calculator. We've got our moles related to the amount of energy, and we've used the molar mass to get into moles, and then my new mole to energy ratio here, and my final answer would then be also negative, a 2.61 kilojoules. Final answer. So this is our new mole to energy ratio. All right, let's try another one. First, let's look at the equation. This time I can see I have lots of different coefficients, so I want to be really careful I'm selecting the right one. And I also can see that I have energy on the product side. So does that mean that this is an exothermic reaction or an endothermic reaction? Something on the product side is going to make it exothermic, meaning that the sign that I'm using should be negative. Anytime I talk about that amount of energy, it should be a negative 1,454 kilojoules. Notice it didn't say minus because it's saying I've produced carbon dioxide and water and this amount of energy. Produced that amount of energy, so it is negative. All right, our given this time, we are producing 1,820 kilojoules. Producing again, so again, the negative sign. Negative 1,820 kilojoules over 1. So I want to get out of kilojoules. I'm going to go ahead and bring that to the bottom. And from the equation, I know I can relate kilojoules to moles. So that'll be my next step. But the question doesn't ask for moles, it asks for mass. But we're pretty good at going mole to gram by now, right? That's our mole conversion. Mole on the bottom, gram on top. So now what I plug into my mole energy ratio has to come from the balanced equation. So what is it that this was the energy of? We're being asked about something called methanol. Now, even if you don't know what methanol is, we can kind of use some deductive reasoning here, right? Well, that's water, that's carbon dioxide, that's oxygen. So this guy must be my methanol. Meth, by the way, means one carbon, and the OL refers to that hydroxide group. We'll get into that in Unit 14. For now, we've got to figure out how many moles of the methanol, which would be 2 here, is proportional to this amount of energy, which is going to be negative, because it's exothermic, 1,454 kilojoules. Then to get to grams, I'm going to use my molar mass. 1 mole, and then here I will put the molar mass of the CH3OH. Plug in the molar mass, and then solve across. So let's go ahead and get that one in the calculator. All right, here we go. So this is kind of showing you can also set it up as a proportion, but then you have to worry about the molar mass separately. So either setup you want to do, the final answer would be 80.2 grams. It takes 80.2 grams to produce 1,820 kilojoules, since 2 moles of methanol produces 1,454 kilojoules. It's all about converting. Let's do one last one. I'm trying one instead of grams to come from liters, but notice it is at STP. So remember that 22.4 liters is equal to 1 mole at STP. We're going to be using that. So starting with talking about the equation, I have my mole ratios. Again, I have twice the hydrochloric acid that I do anything else. And again, I have heat on the product side, making it exothermic. So the fact that this is exothermic means I need to make that number negative. If it were endothermic and the heat was on the reactant side, then I would keep that number positive in my calculations. So what's our given this time now? We have 58.0 liters. So I'm going to put that over 1. And then because I want to get out of liters, I'll put that in the denominator. And since it's at STP, I can now convert volume to moles. The question is asking about the heat, so I'm going to need my mole to energy ratio for my balanced equation. So mole will go on the bottom and kilojoules on the top. So mole to liter at STP would be 1 mole to 22.4 liters. Energy is this 1250, but it's exothermic, which means that needs to be negative. Just because we've changed the amount doesn't mean it's not exothermic all of a sudden. It's still going to be exothermic, and we want a negative answer. Now, how many moles? This was liters of hydrogen. So our hydrogen is right here, and it has a coefficient of 1, so that's just going to be 1 mole. If this were liters of our hydrochloric acid, then we may need to use that 2 coefficient. But the hydrogen is our gas here, so it's got the 1 mole. So now we need to crunch this one in the calculator and figure out how much energy, and notice that the negative sign would still be present in our final answer. So let's get that in the calculator. So again, the PowerPoint likes to show it as a proportion, so because I showed it with the entire dimensional analysis. But notice if we did this much energy, the negative 1250, it would be proportional to 1 mole, but they gave us liters, and so you're having to kind of do these side conversions in your head. Well, 1 mole is equal to 22.4 liters, so let's use that as a proportion. So I'm not as much of a fan of doing this stuff on the side. I like that dimensional analysis. But either way, you get a final answer of negative 3,240 kilojoules. So pick your poison here, whether you would like to do it as a proportion and just be really careful about your units, or use the dimensional analysis that's kind of become like the main part of chemistry, you're going to get the same final answer. Either way though, you have to be really careful about your sign. Exothermic reactions will always have negative heats, and you can tell they're exothermic when it's on the product side, or if it gives you a separate delta H that's negative. Endothermic reactions will always have that positive delta H, and you can tell that because the heat energy would be on the reactant side, or it would give you a separate delta H that is positive. So you've got to translate that and make sure that your final answer gets the correct sign. For this problem, it was negative 3,240 kilojoules. All right, let's move on to our second rule of thermochemistry. If you have a reverse reaction, and yes, that is a thing, maybe you synthesize a compound, but then you could also break it down. So the reverse reaction would have the opposite sign. You can also think about this even with phase changes, where a particle would need to absorb energy in order to melt. It would need to release energy in order to freeze. So when you have the opposite process happening, or the reverse reaction happening, the sign will also be opposite. Oops. So when you have the delta H, you will have the same exact amount of energy, because it is a law of conservation of energy, or there is a law of conservation of energy indicating that that same amount of energy should be used to either melt or freeze. But melting would require an absorbing of energy. And so that would then be a positive 6 kilojoules. Whereas if I'm freezing, I would then need to drop my temperature and release heat, having a negative 6 kilojoules. Notice the amount would be the same, but the opposite process would have an opposite sign. So we can think of this with something called elephant's toothpaste. It's a really good example. You may recognize this from experiments in middle school. When you decompose hydrogen peroxide, you're going to release a lot of energy, and the delta H is negative. But in order to form hydrogen peroxide, you would have to input energy. Notice it's the same amount of energy, but one's negative and one's positive. Now physically look at what happens to the chemical reaction. It's literally flipped. The hydrogen peroxide becomes the product, the water and oxygen become the reactants. So this is what we're going to be on the lookout for other types of reactions. Whenever you see a flipped reaction, you know you have to change the sign for delta H. We're eventually going to work up to doing something where we're flipping equations on purpose. And whenever you do that, you want to make sure that you also flip the sign. So the second rule of thermo is that you're going to flip the sign when you flip the reaction. So let's look at an example to apply this. This is actually going to apply both of our rules, proportionality and the sign flipping. So the reaction we're starting with, that it actually gives us the energy for, is kind of interesting. Let me go ahead and talk about this big elephant on the board here. Half an O2. What do you think that means? Do you think you have half an oxygen molecule, meaning one oxygen atom? Well, that's impossible because oxygen's diatomic. It can't exist as a single oxygen atom. So what else did my coefficients mean? Mole. It uses half as much oxygen as it does the water or the H2 gas. Well, that's easy to fix. If the chemical reaction I'm actually interested in has 1 mole of oxygen instead of half a mole of oxygen, I can just double this entire equation, meaning 1 becomes 2, the half becomes a whole, and then again over here 1 becomes 2. So now my coefficients look similar to the equation that I'm trying to find the heat energy of. The only thing that's different is that my reactants, the hydrogen and oxygen, became the products, and my product became the reactant. So this is also flipped. We flipped it and we multiplied it by 2 in this reaction that I'm searching for the enthalpy of. So everything that you do to the reaction, you also have to do to the delta H. Because the reaction on the bottom here is backwards and doubled, the enthalpy will also be doubled, not divided by 2, sorry. Will also be doubled, so times 2. And because I have it flipped, I'm going to flip the sign. So I'm going to have this positive 285.8 that doubles in order to make 1 whole mole of oxygen. So we're going to do the same to the delta H, and we get an enthalpy of a positive 571.6 kilojoules, because we've got the reverse reaction with twice as much reactants and products, twice as much stuff. All right, on to our third and probably most challenging rule. something actually called Hess's law. So the third rule actually explains that reactions can occur in steps, and the total amount of energy would be the sum of all of those steps. This kind of reminds me of Dalton's law. The total pressure was equal to the partial pressures. Well, the total energy is equal to the sum of the partial energies. Not all reactions happen in one step. Sometimes they take 2 or 3 steps to get to the desired product. So if you can find the energy of each individual reaction, you can then get the total reaction. This is our third rule of thermochemistry, also known as Hess's law. We want to add up all of the steps in order to get the enthalpy of the end product. So let's look at one of these together. This is our goal equation. This is what we would like the two given equations to add up to. Let's see what they add up to right now, just so you can get the hang of adding equations. I'll go ahead and give you a little bit of a spoiler. It's not going to be this guy yet. We're going to have to do things first in order to get this total equation. So first of all, on the left-hand side, I can see I have 1 carbon, and I have 2 carbon dioxides. And then I have 1 mole of oxygen in each reaction, so that would total 2 moles of oxygen. And then on the product side, I have 1 mole in equation 1 and 2 moles of equation 2, so that's 3 total moles of carbon dioxide. So when we say we're adding up the equations, this is literally what we mean. We're adding up all of the total moles of reactants and putting them in one equation, and adding all the total moles of product, putting them in the final equation as well. If anything was on the reactant side and the product side, it would cancel. So say I had 1 mole of oxygen on the left and 1 mole of oxygen on the right, that would mean no oxygen would be in my final equation. So now that you get the hang of kind of adding up, how in the world can we make it add up to what we want? Carbon, half an oxygen mole, and 1 carbon monoxide. I want to do things to these two equations in order to get it to add up to that final equation. Then whatever I'm doing to each equation, I want to do also the right thing to the delta H. The first thing I recommend doing is making sure that you have reactants that you want on the reactant side somewhere, and products that you want on the product side somewhere. I would recommend taking care of that first before you start worrying about how much of the stuff. Because if you have to flip the equation, you're going to have to redo all of that canceling anyway. So let's check first our carbon. I have carbon on the reactant side in equation 1, so I know I'll be able to get it on the reactant side in the end. And then the oxygen I also have on the reactant side in 2 places, so I know somehow I'll be able to get it in the end. But I run into a problem when I check my product. I'm supposed to get carbon monoxide as a product, but all I have right now is carbon dioxide as product. So where do I have carbon monoxide? It's not even present in equation 1, so that can't help us, but it is present in equation 2. So that tells me that equation 2 is going to have to be flipped, because it's the only way to get carbon monoxide on the product side. So what I would recommend doing is actually crossing it out and rewriting it. So it's really easy to get kind of mixed up on these equations. So I've got my carbon dioxide, which there was 2 moles of in equation 2, and then I'm going to bring my 2 carbon monoxides and my oxygen, my reactants, now becoming my products. Because I have flipped the equation, I need to flip the sign. So this negative 566 kilojoules will become a positive 566 kilojoules. Whatever you do to the equation, you have to do to the delta H. Now let's check the amounts. So I see I have 1 mole of carbon and I end up with 1 mole of carbon, so that's good so far. I can see I need half a mole of oxygen, and right now it looks like they would cancel completely. So let's hold off on attacking the oxygen. Let's look at the carbon monoxide. In the end, I only want 1 mole of it, but in the only place it exists, there's 2 moles of it. That tells me that that equation is going to need to be cut in half. So multiplying this equation by 1/2, or dividing it by 2 basically. So half of the CO2, where there was 2 moles, would become 1 mole. Where there's 2 moles on the product side, it also becomes 1 mole. Now here's the tricky part. The coefficient of oxygen was actually 1, which we didn't write. We just understand that it's 1, right? So what if we cut 1 in half? Well, then you get a half. So that's going to take care of multiplying by a half or dividing by 2. So that means I also need to do that to my enthalpy. 566 divided by 2. A positive 566 divided by 2. Because what I did to my second equation was divide by 2, or multiply by half, and flip it. So we want to kind of note that to the side. This is going to help you get partial credit also. Note that to the side, and then show that happening on your delta H. So that way when you get to the end, you can still figure out how to get the final answer. Let's make sure that this works. First of all, on my reactant side, I have 1 carbon. And then on my reactant side, I'm supposed to only have half an oxygen. But here I have a whole oxygen. Well, that works actually because, let me use a different color here, not red. Half an O2 will cancel proportionally with half an O2. On the left-hand side, I have a whole O2. So if half of the O2 cancels, that would leave the other half. So this goes away completely, and this now goes down to the half O2. So that's going to work out great for my end result here. So what I have on the left-hand side is the carbon and the oxygen, but I also have a carbon dioxide. I don't want that in the end. So let's look at our carbon dioxides. Well, there's one on the left and one on the right. So 1 mole of carbon dioxide would cancel with 1 mole of carbon dioxide evenly. So you cancel exactly as much as exists, and if they are the same, they cancel completely. So that's great. We have our reactants kind of figured out. As for the product goes, the only thing left here is my 1 mole of carbon monoxide, which is exactly what I wanted. So I know I have now manipulated my 2 equations in order to get them to add up to the goal equation. What is it that I was trying to find the total energy of? I made sure to make the changes in the delta H as I went, making the 566 positive and then cutting it in half. I want to take that number and add it to this negative 393.5. Notice we didn't do anything to the first equation other than let it cancel out. That doesn't indicate any kind of changes for the delta H. Canceling would happen naturally. So I just need to combine those enthalpies. Careful with your signs because one's positive and one's negative, and then we can get our total delta H of a negative 110.5. All right, showing that the second equation was cut in half and flipped, that my carbon dioxides canceled, that half of my oxygen canceled. So I've done the appropriate changes to the delta H, got that final answer. Let's try one more of these. So now I have a new goal equation. Now I'm trying to figure out how to make NO2. And these are my steps. My first equation produces NO, my second equation produces NO2, and I have the individual enthalpies. Missing some units here. So then what can I do to these equations to get them to add up to the equation I'm trying to find the enthalpy of? So the first thing that I'm going to do is write this at the bottom so I can think of this addition linearly. So I'm trying to get NO and half a mole of oxygen as my reactants, and then 1 mole of NO2 as my product. So let's first make sure everything exists where it should. Do I have NO on the reactant side? Ironically, no, we do not have NO on the reactant side. The only place it exists is over here on our product side, which tells me I'm going to need to flip this equation. So I'm going to write NO on the left and my half nitrogen and half oxygen on the right. When I flip that first equation, I need to flip the sign, meaning my positive sign needs to become negative. It's not positive 90.4, it's negative 90.4. Now do I have oxygen on the reactant side? And I do, just not exactly the amount, but that's okay right now. And then do I have NO2 on the product side? And I do. So once you make sure you have everything on the correct side, now we can start looking at, do we have the right moles of everything? So I only want 1 mole of NO, which I have. I want half a mole of oxygen, but I have a whole mole of oxygen. So let's look at the product side. Over here, I have half a mole of O2. So that's going to cancel with half of this whole mole, leaving the other half. And now that'll match. And then the NO2, we have 1 mole, we want 1 mole, we're good. There's also the problem of the half N2, but notice one's on the left and one's on the right. So they're going to cancel completely, which is why they don't end up in the product without having to do anything else. So all we really did is flip the first equation, which means we just need to make sure we're combining the negative 90 with the 33.6. So what do we get for our final answer this time? A negative 56.8 kilojoules, showing that that flip of the NO equation is now going to be a negative 90, which when you combine with the positive 33, you get the negative 56. And we are adding, so we're going to keep the 1 decimal place, negative 56.8 kilojoules. All right, so there's no quick way to work these Hess's law problems. It's kind of trial and error. My best advice is to make sure that you have reactants and products where you need them before you start trying to figure out the amounts. Look at what cancels, make sure that you're canceling proportionally, and then be really careful that you're keeping track of the enthalpy as you go. You're much more likely to make mistakes if you go back and try to remember what you did than if you mark the changes as you go. So that's my best advice for Hess's law. Before we wrap up these notes, I want to go over 4 very important laws of thermodynamics. Ironically, they don't start with number 1. The first law of thermodynamics is actually the 0th law of thermodynamics. The 0th law of thermo will define temperature as the average kinetic energy of the particles. This is kind of what gives us that Kelvin scale, giving us what temperature is really designed to measure. The first law of conservation of energy is actually also known as the law of conservation of energy. It simply states that energy cannot be created or destroyed. The second law of thermodynamics is probably the one we're going to talk about the most later in Unit 9. And according to the second law of thermodynamics, entropy will naturally increase. So I like to paraphrase that by saying nature loves chaos. Things will naturally become more chaotic. In order to increase the order, you would have to input energy to the system. And that's a big deal as we talk about our next set of notes. But let's go ahead and finish this up with our third law of thermodynamics, which defines absolute 0, or 0 Kelvin, as having absolutely 0 movement and 0 entropy. So no average kinetic energy would be 0 temperature, 0 Kelvin, and then that also would have no chaos since there's no motion. So S is actually the symbol for entropy, and then you should recognize delta H now as enthalpy. These are all 0 at absolute 0. So that's our third law of thermodynamics. So I want to make sure that we know these and can apply them to actual problems. All right, guys, that's going to wrap up Notes C for Unit 9. Our next set of notes will be Unit 9 Notes D, where we're going to talk about phase changes, and we're going to talk about the heat of formation. We'll see you there.